Hello everyone, welcome to the 10th episode of Math and Beyond, and in this podcast. Today we are going to talk with Uddipta. This is a tough name for me to pronounce. It is, sorry, I made a mistake. Uddipta Bhardwaj, I think. He's a PhD student at Grappa, at the Institute Grappa here in Amsterdam, and he's doing his PhD in gravitational wave detection and developing some parameter inference approach using machine learning. It is very interesting and, let's say, cutting edge topic. So we will debunk it. We will delve into it, and I will send him the invite now. I will see you shortly. Hi, Uddipta.
Hey, Francesco. How are you?
Hi, how are you?
Good.
Great. Are you at Science Park?
I am at the institute. Yeah, it's near my office.
Okay. Yeah, they are keeping you quite late Friday afternoon.
Totally fine. No worries.
It's okay. Yes, I'm also at school, and there is a very good sunshine, so I decided, let's go pick up a room where I can sunbathe a bit while I'm being told about gravitational waves.
Why not? Nice.
Exactly.
Yeah, nice weather today. It's really nice.
Yes. Also, this weekend, today, tomorrow, and also Sunday, there are 22 degrees max, so it's very nice. Actually, tomorrow I am going to Keukenhof, which yes, exactly, the big garden with tulips and stuff. It's very, very, very pleasant garden. I see some picture. It is amazing. It closes on Sunday, so these are actually the last 2 days available. So absolutely, I gotta have a look at it. Okay, so I gave a small introduction about you. I said you are right. You are pursuing your PhD now at Grappa, at the Institute Grappa from the University of Amsterdam, and your research area is indeed gravitational waves, and you are applying machine learning for inferring parameters of indeed gravitational waves. And we are going to talk about this more from a theoretical maybe perspective, and then we will delve onto the details of your research. So I would say that we can jump into it, and I will ask you gravitational waves. Maybe some, let's say, physics and astronomy geeks may know some, let's say, big news from recent years that they have been detected for the first time. But what are they? What can we learn from these waves? Because we know that we have, we see through electromagnetic waves. We have the visible spectrum that we can see, but we know that there are many more wavelengths that we can observe, radio, gamma, whatever. But what are then these other type of waves? What are gravitational waves? What we can learn from them? What physical properties do we know?
So that's again. So for the first time, if I describe gravitational waves to anyone, so essentially, the fact that distinguishes gravitational wave from a standard electromagnetic wave would be that you would study an electromagnetic wave with respect to a background. So you'll have a background, and then there's some perturbation on top of that background. In terms of gravitational wave, the background here is not well defined because the perturbations are in space-time itself. So it's space-time perturbations that's caused by some highly explosive or energetic phenomena. And essentially, in principle, all you need to produce gravitational waves is some acceleration and some asymmetry. Those two are the only ingredients that you need, in essence.
What do you mean when you say? Sorry, if I can interrupt. What do you mean when you say asymmetry? Can you briefly expand on asymmetry? Why do we need asymmetry for gravitational waves?
So you need some sort of symmetry to be broken. Otherwise, what happens is that Let's say, for example, if we talk about gravitational waves propagating through space-time, that you have what happens is basically the space-time curvature changes. In essence, that's what is happening, right? There's a change in space-time curvature. In a symmetric system, the space-time curvature would be maintained, and that change would not be noticeable. That asymmetry information is encoded there. And so basically what we detect, but then the thing is, there are different types of gravitational waves that exist all over in our universe. But what we have detected till now is essentially only from one type of kind of source, which is by the merging, phenomenon. So which is the merging of two very compact objects. So two really massive compact objects. And you need them to be massive, not in order to produce gravitational waves, but to produce gravitational waves that are detectable by the present day instruments that we have.
Okay. And you said before there are many types of gravitational waves. What do you mean by that?
Currently, in terms of like the search efforts and the information that we have in terms of building these detectors for gravitational waves, what we know are, let's say, 4 distinct categories of phenomena that are producing this kind of waves. One of them, which is the one that we actually have proof of that has been detected, is the binary coalescence. The phenomenon is called coalescence. Coalescence basically means two things that are rotating along each other, and then they kind of spiral in. So their orbits shrink because of gravitational attraction, and then they get closer and closer and closer, and at some point they merge. So this phenomenon of getting closer to each other in spiraling is called coalescence. So that's the only phenomenon that has been detected actually, but then there are 3 others. One of them is continuous gravitational waves, which is produced by, let's say, again, a very compact object that's rotating by itself, isolated. So it'll produce something that's like let's say, a harmonic oscillator kind of frequency. It's not the standard, like in spiral, the signal, typical, if you Google gravitational waves, like the typical signal that you will see, which is like going to a chirp, like a peak, and then it goes down, right? So it's not like that, it's continuous. Another one is the stochastic gravitational wave background, or the stochastic gravitational waves, which is basically remnants from early universe evolution. It's similar to, or analogous to, what you would say is the cosmic microwave background, for example, the CMB. So similarly, you have like a stochastic gravitational wave background. Again, these are theorized. There's enough, let's say, theoretical basis for these things to exist, but not empirical evidence yet, not observed yet with the current facilities. And another one, the 4th one, is bursts. So it's, again, some sort of very explosive phenomena, but that doesn't happen across time. So for example, in the compact binary case, you see in spiral, you see merger, and you see ring down. So these are like 3 distinct categories, which is in spiral is when they're coming close to each other. You see a gravitational wave already from that point. Then they merge, where you see the chirp or the burst signal. And then the remnant kind of spins down to a stable state, which is the ring down of the gravitational wave. So you see in spiral, merger, and then ring down. But in this case, in the burst case, you only see like a very short, it's highly transient. So you see it for a very short time. So it's another like extremely explosive phenomena. And there's some sort of this thing that induces these changes in the space-time curvature, and you see a gravitational wave. But then this might happen over a range of frequencies. It can emit gravitational wave over a range of frequencies, sure. But in terms of time, it happens on like, very small time steps. And that's what happens. So that's the burst gravitational wave. So these are the 4 standard, like the burst, the compact binary coalescence, the continuous, and the coherent, the stochastic gravitational wave background. So these are the 4 main ones. And I would say possibly in like the next 20 years or so, we might have evidence for the other types as well, apart from the standard binary coalescence thing.
Okay. But okay, now let's say a question that may follow logically from one that is not very keen on gravitational wave is okay, we have been let's say listening and seeing electromagnetic waves from many years, many decades now, and we know what properties we can learn from electromagnetic waves. Can you list like I don't know, so, literally a couple of properties that we can infer from electromagnetic waves,
Yes.
like the composition or literally exactly chemical whatever. Okay, so the thing is, why do we want to search for gravitational waves? What properties, physical properties of these, as you said, explosive events? What can we infer from them?
Mm-hmm. So yeah, this is actually a very cool question to think about, mainly because I have a job, because there are things that you can actually find out from gravitational waves, because I do something right in the middle about getting that information and actually existence of gravitational waves, right? So what I do is inferring parameters, which would then, after we established that, okay, there are gravitational waves, they are coming, we detect them, I do the middle part, and then people do, let's say, astrophysics or whatever they want to do with that information. So the main point here is that, again, there's a lot of stuff to do. First thing, since this is a phenomenon that involves gravity, by virtue of that, it contains information about the masses involved. Whenever you have something with masses involved and you're talking about gravity and space-time curvature, you can do tests of, let's say, GR or any theory of gravity, right? So you can do, you can actually test the validity of the general theory of relativity, how, let's say, space-time curvature behaves in, or like any kind of motion is treated in extremely strong gravitational regimes, because these are highly massive objects that we're talking about, like black holes, neutron stars. These are extremely massive, so very strong gravity. What else you can do is, if they have, let's say, one of these binary things, so I'm talking in the context of binary. So if one of these are, let's say, not a black hole, let's say a neutron star or something like this, then there's associated electromagnetic waves that can also arise from that. So, but you have the gravitational waves kind of first, you know that, okay, these are, let's say it's in spiraling, right? As I say, they're going to merge. They have not yet merged. And then at the end they merge. So if you can know, okay, these are in spiraling, there's a gravitational wave that we have detected from this, you can tell your electromagnetic telescopes, like, hey, there's an interesting thing happening there. There's a gravitational wave that just came from this location, point your telescopes there. So you can turn there and look at electromagnetic jets coming from there, which will tell you information about how the interiors of these stars, these kind of dead stars, let's call them, neutron stars and stuff, what kind of physics that's going on there, the magnetic fields involved in their environments, all of these things, the density of the environment, all of these things. Then there's also conclusions to be made with this very cool term that I like to say, which is the standard siren thing. There was a term coined recently, and the standard siren is basically...
sorry, the standard?
So standard siren. So siren as in like the police sirens, like the thing that you have on the police cars or the
okay.
Standard siren, because the gravitational wave is also essentially what you listen. You don't really see a gravitational wave, right? You kind of listen to it.
Okay.
Like
the sound wave that we listen from the siren of ambulance or police.
Yes. So it's kind of like an ambulance, or imagine it passing by. So that's kind of what happens, right? It kind of increases in volume and then it finishes.
Okay.
That's similar to what you see, like a very rough analogy, but in terms of, let's say, naming things, that's totally fine. And why it's called standard siren, because this is analogous to like the standard candles approach, or so basically what happens here is you can use gravitational waves to infer properties about the cosmological scales of the universe, or cosmology. What that entails is standard siren method is used to basically understand the value of the Hubble constant, for example. And now I totally understand that for this, you need very precise measurements of properties of the sources. But nonetheless, this is a very exciting avenue to study the Hubble constant, the other cosmological parameters, basically, which tells you what's the history of the universe, basically, and all these things. And then if you bring into account like all the other types of gravitational waves, or this phenomena like the stochastic thing and all these things, then there's even more information that's encoded there, like about, let's say, the early evolution of the universe and all these things. So, I mean, we are at the very, very beginning of the gravitational wave universe, let's say, because, for example, think about astrophysics that is done with, let's say, galaxies or stars. There's billions of stars that have been like cataloged till now. Millions and millions, even maybe billions of galaxies that have been cataloged, right? So we have information about so many galaxies, so many stars, and people are still finding out information about them from these catalogs. You have only 90 gravitational wave sources that have been cataloged, like 90, and then there are some sub-threshold sources and some other catalogs, but let's say about 90 to 100. That's nothing compared to, like, you know, order of millions and billions. So yeah, so given that we actually keep detecting these gravitational waves, and of course, I think with improvements in detection capabilities, we are going to detect more and more. There's a lot of physics to be done, yeah, with gravitational waves.
What a time to be alive. What a time to be a physicist.
Amazing time, yes. Amazing. It's been only 8 years since the first detected gravitational waves, not even, right? 7.5 years. And look at what happened. Yeah.
It's great.
Yeah.
Great. Yeah. But you said before, we can learn properties of our universe. And now this is maybe this is a $1 million question, but what do you think, let's say, what do you think we can infer about the Big Bang through gravitational waves? Because we know it was such, let's say, a disruptive event that it surely, like, even just by, I'd say, by logic, it surely must have left a trace, at least with regards to the stretching of space-time, as you said. It surely must have left a trace. What do you think, can we learn something about it? Because you said, yes, we can learn about the history of the universe, but I would say the $1 billion question of cosmology is the Big Bang, is the precise moment of it. What do you think? Yeah, what about gravitational waves and the Big Bang?
So the physics coming from that would be encoded in something like the stochastic gravitational wave background, for example. I can't say the amount of, like, or what you can infer from that already, because it has not yet been actually observed. But there are theories that people have lots of papers out there that actually claim that these are the things that we can understand and these are the things that we can analyze. But for sure, if there's physics from cataclysmic events happening in the very, very early universe that leave traces that are still observable. In particle physics, the observations of the cosmic microwave background changed the whole realm of particle physics, right? There were so many experiments, like Planck is still doing their stuff and all these things. So I think there's a lot to do there. Even with compact binary coalescence gravitational waves, you can already infer properties by independently, because gravitational waves gives you an independent measurement of the distance. You're not using electromagnetic information, you're using just the gravitational wave to get ideas about how far away the source is. And if you know how far away the source is, then you can use that with like other standard distance calculations, which does involve an underlying cosmology, so some redshift and the Hubble constant basically. And you can use these Hubble laws to actually calculate the Hubble constant. And even getting information about the Hubble constant can give you a lot more information about the early universe, because just by virtue of, you know, what it entails, what the Hubble constant explains basically.
Okay. Yeah, hopefully we will be able to see some major breakthrough in gravitational wave detection, to which now I would like to turn, and because we covered pretty much the basics, the very basics of gravitational waves and properties, but now let's turn into gravitational wave detection. We know that, let's say, I would say the most famous center for detecting gravitational wave is at LIGO, Laser Interferometer Gravitational
Wave.
I don't. Yes. Okay. And what are they doing there? Can you how do they detect the gravitational wave? How do you detect a gravitational wave?
So yeah, that's a great question. I can give you like an overview of that. So basically, yeah, that's the premier collaboration that does this. I'm a part of that as well. So it's the LIGO, let's say now the LIGO Virgo Kagra collaboration. And it's not just one detector, but a network of detectors. So there's these LIGO centers, the LIGO interferometers, and because the name, as the name suggests, the I in LIGO, the LIGO, right? The I is interferometry. So what it does is by the principle of interference, right? And what happens is that for now, we have a network of detectors. I will come to that, like why we actually need that. But the whole point is, let's say there's two LIGO detectors in the US at two different places. There's one in Italy, which is Virgo, and there's things being built in Japan, Kagra. There's the one coming up in India that's going to be built, LIGO India, and so on. So this is going to be like a network of all these detectors. But till now, the active ones are the two LIGO interferometers and Virgo. And so the basic principle here is interferometry. So what they do is, it's extremely technical. So it's very engineering heavy. As you know, that the frequencies at which these gravitational waves are emitted, the bandwidth is pretty large. So it's emitted across a range of frequencies, and we cannot access the entire frequency range of gravitational waves yet. Not because we cannot observe in those, but because there are lots of noise sources in those on Earth. Let's say, for example, one of these examples would be like a car passing by. You cannot stop a car from passing by the road. That already creates noise, which is at that dominant in that frequency range where you might observe some part of a gravitational wave. So that part, if there's a car passing by at the time that you're observing a gravitational wave with LIGO, forget about it. Your data is gone. So things like this. So it's highly sensitive to all of these things. Even thermal noise, for example, if it's a hot day, there's a lot more molecular movement in the air, gone, so on. So it's very sensitive. So they use lots of cooling layers. They use like these cryogenics. They use incredibly complicated mirrors that are suspended from, again, in order to reduce this shock noise. So they're shock absorbers and all these things. So what they do is they have these very long arms, like kilometer long arms, very, very long. And the ones that we have now are L-shaped. So there's two arms perpendicular to each other. And these arms, let's say, are like straight lines about a kilometer or so long. And they're lasers that are pointing to sorry?
I think I saw a video recently at in the two locations in the United States. I think they were 4 kilometers, the arms.
No. It's two arms. So it's two arms, but they send the laser twice. So that's why it's like 4. It works like 4 because they reflect the laser and send it again. So it's like covers it 2 times, covers the length, but it's actually 2 arms. And then there's the node in between where the 2 arms meet. So
but I mean the length of the arms.
Oh yeah, length of the arms. What do you mean?
I said I would say I said the length of the arms was 4 kilometers. So meaning you have
no, for sure. That's correct. Yeah, and then that's different for different interferometers. Like Virgo is slightly different, and LIGO is different, and so on. But so what happens is that these lasers, since they're maintained at a very cold, stable environment, and then what they do when they meet is because there's like an interference pattern that's produced, right? Because of these two lasers meeting. And what happens? So what happens in interference pattern is that you can relate it to the path difference or the path length of the light beams that are causing this pattern. So if there's any change in the path difference that the lights have to travel, the interference pattern changes. And this change in interference pattern is what you measure. If you can account for all the reasons that's causing this change in the paths that these lasers have to travel, all the causes, let's say there's some small perturbation because of an earthquake. Okay, we know how this happens. Let's take that into account. That's done. Then there's a car passing by. This is a street. This is the detector is located in this place where nearby there is a street where there are trucks that go by. Let's take an average over a year or 10 years, calculate this, take that into account. So after eliminating all these local sources that can cause a path difference, what's left is basically this gravitational wave. Because gravitational wave stretches and squeezes the space-time itself, it changes the path of the lasers or the path that the light has to travel. So because of this delta path, it induces a delta interference pattern. So the interference pattern slightly changes. And this change is your gravitational wave. So what we observe is a strain, basically. So it's a relative change in the path length or the relative change in the path. So that's the strain signal. And the order that you would measure from the typical range of the masses of sources that we are getting from the LIGO Virgo gravitational waves that have been detected so far is of 10 to the power minus 21. So you can see how sensitive these strain measurements are, right? If you can
and
measure.
when you mean when you say 10 to the minus 21, you mean 10 to the minus 21 of a change in the wavelength of the laser. Okay.
Yeah, the fractional
so
change, 10 to the minus 21.
Okay, so pretty fucking small. Okay.
Extremely precise. Like, and that's like a good one. So it's highly precise, and that's also seen between like a range of 20 hertz to about 1,000 hertz, so about 1 kilohertz, or let's say 2,000 hertz. So order of 1,000 hertz, starting from 20 hertz. That's the bandwidth at which you can observe. Ideally, you would observe something, let's say, at lower frequencies and also at higher frequencies, because let's say if there are some extremely massive black holes that are merging and producing these gravitational waves, essentially what happens is that if they're very massive, it's a bit slower, the evolution and stuff. So what happens is that they emit these gravitational waves at a lower frequency, and we totally miss them. And if they're like extremely small masses that are also producing, then they can be faster. The frequency is even higher. We also miss them. So we have a very selective bandwidth where we actually detect these sources. And on top of that, we have all these noise problems and all of these things. In spite of all that, which is why this detection was such a big deal in 2015. In spite of all that, like there have been 90 already. And then now the fourth observing run is going to start sometime this month, or maybe next month, I think this month. And we hope to, by the end of the year or next year, to learn about more new sources that have been detected and so on. That's the hope. So, yeah.
Okay. Why do we have such a small bandwidth that we can observe?
It's just because of the noise characteristics. So because these are not perfect detectors. Ideally, we would have a detector that when we don't have a gravitational wave, it just outputs 0, right? So ideally what you would have 0, 0, 0, 0, 0, 10 to the minus 21, 0, 0, 0, 0, 0.
Okay.
Perfect, but that's not the case. There's a lot of noise. And somewhere within the noise, there is a 10 to the minus 21 fractional gravitational wave that's lying there, right? And you have to dig, clean up, think about all the possible noise sources, try to get rid of them, and then see, okay, there is something there that looks like a gravitational wave. Yeah.
Okay. So you just said before 2015, we have the first detection of gravitational wave. What does we gotta mention the fact that out of this detection, 3 Nobel Prizes have been awarded: Kip Thorne, Rai, Vance, and Barrett. Yes, another guy at LIGO. What does this represent? Why is it such an astonishing achievement of mankind? And yeah, why is it a milestone? And and actually, what does it? Let's say, yeah, what is its significance in astronomy?
So first thing in itself is the actual validation that these things exist. This was predicted in 1915 by Albert Einstein in one of his papers. Exactly 100 years later, somewhere we detected this, right? Talk about delayed gratification.
Quite ironic, 100 years later.
Talk about delayed gratification. That's 100 years. So finally that already was a big deal for people interested in gravity and GR and physics and so on. Then came all the aspects of the information that this entails. It encodes information about space-time curvature, gravity itself. So you can actually test whether Einstein's GR is a great theory, which works everything. Of course, it's a great theory. It's one of my favorite theories, so I'm biased. But if it's actually if it actually works across all regimes in all scales that are involved, so let's say in like very strong gravity scales and also at long distances and so on. So all of these things. And then there's the case for these associated electromagnetic observations. Then there's cosmology. So there's essentially like a lot of physics that can come out of this. But the biggest thing would be to have empirical evidence of a theory that has stood the test of time from, let's say, for 100 years. And then it was like a fall moment, when it was actually detected, everyone was like, oh, wow. So this is actually something real and not just, people going crazy over it.
Can I ask why is it your favorite theory, GR?
Oh, I just love it. I think it's very beautiful. It's one of the theories that has been corroborated. I tell every time when I teach a student like a GR or gravity or something, my first suggestion is study this theorem called the Lovelock's theorem. So there's this beautiful theorem in mathematics.
Sorry, can you repeat that?
Lovelock. So Lovelock. Lovelock's theorem. And Lovelock's theorem basically, I think, decorates GR in a very nice way. It gives beautification to it, basically, in terms of, let's say, it provides the uniqueness to the theorem. So I definitely want you to read it, and it will really help you understand GR in a much better way and have a nice appreciation for it. Plus, it has stood the test of time. I mean, if we just speak heuristically, it has worked for so many years and it's still entirely valid. Like, there hasn't been another theory that's so consistent, such as GR. People have tried to modify GR. There's lots of modified dynamics that people study, modified gravity theories with augmentations to GR, or completely new theories that people study, but it doesn't have this span that GR has of validity, working across all scales. And the uniqueness that Lovelock's theorem provides, that says that this is not just a theorem that works, but it's also the only theorem of this kind that works. And that's, I think, a very powerful and incredible statement. So, yeah, I mean, this is something really cool.
Yeah, and I believe it adds some, let's say, I would say, fascination is is the thing that we know that the big two theories of the 20th century, general relativity and quantum mechanics. So whereas quantum mechanics has been, let's say, developed and contributed by many throughout, from Planck initial contribution all throughout to Bohr, Schrödinger, Dirac, Heisenberg, Pauli, and all throughout the time. General relativity basically out of the genius of Albert Einstein. And the other thing which I really I tend to do very much if I like to study a subject, is really going at the very root of a topic of a subject. And what one really, I'd say, have to grasp forcibly by general relativity is that it is literally a geometric theory. It is a theory about geometry. Literally. And I say, what is that? And I swear it. I do understand people like you saying it is very fascinating because it. I believe the surrounding. No, actually not the surrounding. What it entails about such a fundamental thing. So literally the thing we are inhabiting and everything that we see that inhabits this thing, the space-time, how it curves, how it bends, how it behaves, the geometry. Okay, and so it is now I just think about it. It is like an analogy of someone writing out a map, saying, "Look, the map is done this, and that way. Okay, this is where we are. This is how this map is done." And I do really agree. It is very fascinating. But
it's a framework for a lot of physics, in the same way that a map is a framework to a lot of things that happen, right? So it's incredible.
What do you think? What do you think we can expect? You mentioned before that we will eventually, likely, very likely, we keep on seeing gravitational wave. What do you think we can expect from gravitational wave astronomy? Are there any, let's say, huge leaps that within 20, 30 years we may be able to make in gravitational wave astronomy?
One of the cool things that's coming up in like that kind of time scale, about 10 to 20 years, would be some of the new detectors that are being proposed, right? So these are new detectors, as in, like, they call them 3G detectors, or the third generation of detectors, right? So now the second generation of detectors is what we have right now. So upgraded from like the initial LIGO Virgo setup. But then the third generation would be something completely different. It's a huge upgrade. One of them is like a ground-based detector known as, a prominent one is known as the Einstein telescope. That's been proposed. The Netherlands, which is where we are right now, is also heavily invested in this. So a lot of European countries are. And then this Einstein telescope is basically supposed to be like a triangular interferometer. So instead of having this L-shaped, these two interferometers, it's a triangle. And it's also not exactly like a closed triangle, but it's like triangular, let's say an equilateral triangle of like 60 degrees, two arms here, then two arms where one of them overlap with the other, and then two arms here. So it's like it's an interesting, it's three angles that exist like this in a way, you know? And then,
okay.
So it's, so that's how the triangle is formed. And then there's another triangular interferometer that's going to be up in space called LISA. So that's the laser interferometric space antenna that's going to orbit around the Earth. And that's again, another incredible thing. So the new thing about this, so people might ask like, why another interferometer, or like why more interferometer? One easy answer would be in the same answer as to why another telescope, right? Modern technology, better improvements, let's get another one. But that's not necessarily the case. That's one of the reasons. That's like the null answer, like the 0th answer, but there's more. More is like, we are now going to explore, especially with Einstein telescope and LISA, let's say LISA, a completely different frequency range, a much lower frequency range. So LISA would be highly sensitive in a frequency range of, let's say, millihertz, or maybe even lower, I'm not sure, millihertz to about like 1 hertz or something like this. So around this range. So this is the range, this very low frequencies, is where these extremely massive objects would merge. Let's say supermassive black holes that are in the centers of galaxies, something like this. And at some point that they merge. And by virtue of it being in space, because of these, you need to be in space in order to be able to listen to these frequencies, because in Earth, there's a lot of noise at these ranges. But the fact is that that's what is going to happen, and it's going to probe distances that are very, very far away. So the proposed sensitivities of these future detectors is going to be much better than what we have currently, which is only natural because it's in the future, right? And what we're going to observe is sources from very, very far away. And the further we go, the more towards the past we are going. So we're obviously going to get information from earlier and earlier in the universe, which then tells you more about how the universe has evolved since then. It can give you comprehensive information about, let's say, if we detect a lot of sources of this kind from all times in the universe and so on to much further distances, you can, let's say, have comprehensive information about mass functions and so on. So it's just a typical example that I give. Let's say, you know, the mass function of how black hole masses have evolved, for example, or how, so basically all these things. So for this, you cannot just make these claims with only 90 sources. You kind of can, but you will get like incredible errors. So they don't really come in handy. But if you have a catalog with like thousands and thousands of these sources, then you can actually make a reliable, precise prediction. Plus, exploring this kind of massive objects and so on will be a completely new regime that we have not, it is yet unexplored. Observing things like, maybe since LISA is in space, maybe we can get detections, which they're already proposing. They might be able to detect, let's say, the stochastic gravitational wave background. So imagine how incredible that would be. That would be like the next big thing, I would say, in gravitational waves. If we actually detect that, then as we have already talked about, like information about the early universe, all these things, it will be as monumental as the first detection of the CMB or the first observation of the CMB, right? So that will be something incredible. So so these are like the next big things that are going to happen in, like, say, the 10, 20 years of gravitational waves, apart from the ongoing things as well. And there are lots of improvements, not only in terms of the sensitivities, but also in terms of configurations. There's a lot of research that goes on. So one of these is the triangulation. So triangulation basically helps with, so now instead of having just one node or one interference pattern that you observe because of this L shape, now you have three, just by making it a triangle, right? So three independent observations of the same thing makes it much better than having one, because first of all, you can 100% confirm that this is not something that is mimicking a gravitational wave. So some like detector artifact that just randomly happened out of nowhere, right? And your mechanism just failed. So you don't have enough technology to know whether this is actually a gravitational wave or just some person went by his bike and did a wheelie, and the frequency was exactly the same as a gravitational wave, something like this. It's better if you detect the same thing in 3 independent places. So that's one advantage. Another with LISA is that it's in space, so there's a lot of noise that you kind of get rid of from Earth and so on. So all these things. So yeah, these kind of small technological changes and obviously major design changes in terms of sensitivity and stuff is going to change the game in like the next few years. Yeah.
Okay. Now, which by the way, the fact that you mentioned having 3 different separate and independent nodes where we receive a signal makes it more reliable. Reminds me of how they sort of built the first or the second image of the black hole. I saw the interview of the guy, and they said, yeah, so basically we gathered the data and we distributed among them, I think 2 or 3 or a couple of different groups who worked on those data. They came up with the image and they compared it such that, and I'd say they separated them completely. They were not in touch. They were not discussing between themselves, so they could not be influenced among each other. Yeah. They came up with the image, and either 2 or 3 images, they were exactly the same, and they said, okay, this must be the case. So I understand. I understand what you say. Okay.
100%. Okay. In terms of detection for gravitational wave, there's this flag. It's a typical. It's a flag called P astro, or probability of this thing being actually of astrophysical origin. And this thing, when you calculate this thing, you give a value between 0 and 1. Basically, if it's somewhere above 0.5, you will say, okay, this is an actual gravitational wave. But when you actually calculate these values, you also take into account how many detectors it is being detected on. So if you have a gravitational wave that's been detected in, say, LIGO Hanford is one of the sites, and let's say also LIGO Livingston, and also Virgo, great. So you can say, okay, safely, that, okay, you won't have a coincidence on 3 detectors at the same time, right? So let's say, okay, this is the thing. So these are things basically to give you confirmation that, okay, this is actually a gravitational wave in terms of detection. And then also in terms of inference to get the parameters and stuff, there's more information there because you're now not stuck. So for example, if you're looking at not stuck by the same noise realization. So let's say this is a technical term, but let's say if you have a detector, a gravitational wave there, and there's a lot of noise there. Now, on another detector, there will be different noise, but it's the same gravitational wave. On another detector, you have different noise, but again, it's the same gravitational wave. So now you know that these noise features are not our features of interest. We are not interested in this. We are interested in the signal features, which is what is kind of being constant across the detectors because the source properties do not change. So they are being constant across the detectors, but then the noise properties are changing. So you actually know. Ideally, you would know perfectly, right? That this is the signal, this is the noise. That doesn't happen. But essentially, you have some idea of what looks like noise and what looks like a signal. If you have it concurrently on detectors with different noise, basically. Yeah.
Okay, so basically you are what they're trying to do to spot, let's say, spot the pattern among the chaos. Okay.
Yeah.
Okay. And now I would like to turn onto your research area, what you're doing. And I want to ask you, you said you are working on parameter inference. And I want to ask you, can you debunk what is said simply in simple terms, what is parameter inference and why does it matter for gravitational wave research?
So parameter inference is basically this let's call it this black box that exists. And if you provide this black box with a gravitational wave, it tells you the properties of the source that's producing this gravitational wave and all the systematics that are involved in between. So depending on what parameters you choose. So let's say for a compact binary coalescence kind of source, this CBC in short, which is basically these 2 black holes or 2 compact objects merging. If they're producing a gravitational wave, you pass it through a parameter inference pipeline, and what it spits out is basically what is the mass of the first black hole, the mass of the second, I mean, the bigger black hole mass, the smaller black hole mass, or whatever the masses are, how fast they're spinning, how their spin angles are oriented, all of these things, how far apart the system is from Earth, where is it, like the location and all these things. Yeah, all of these things. So it gives you all the information that you need essentially to do the physics, because having the gravitational wave itself it doesn't tell you much, but actually getting the physical properties out of it involves parameter inference. And what inference, how it is done, is basically a technique it's basically through Bayes' law. So we use this Bayesian theorem where you have, let's say, some prior knowledge that you give. You can be totally agnostic and give something like a uniform distribution. So let's say there is a parameter that goes from 0 to 1. So it's somewhere in between. You don't know what this value is. You choose, you sample, let's say, 1,000 or 10,000 of values between 0 to 1. And that's your prior distribution. It's totally flat. There's no assumption of a certain shape that you're assuming or giving more weight to some range than the other. You're assuming something totally flat between 0 and 1. And what you do then is you write a likelihood function. So a likelihood function is essentially a function that tells you, given this set of parameters from this sample that you just randomly sample from this sample, how and the data that you have, how likely is that this data is correlated to these parameters? Or basically what it tells you, this likelihood function, is if these are the set of parameters that you have, then how would your data look like? So the probability of, it's not right to say probability because it's not a normalized quantity, but it's like the probability. It's like the probability of the data that you have in front of you given a set of parameters. What you actually want is the probability of the values of all these parameters given the data that you have, because you have the data, you don't have the actual values of the parameters. That's what you want. So in order to get to that, you need the reverse. So if we have a random set of these parameters, how would the data that those random set can generate looks like? And you have the prior distribution. So all of these things is what you need in order to basically do this kind of inference, this probabilistic inference. And what you get at the end is some probability. Let's say you start with a prior completely flat from 0 to 1. And let's say the actual true value is 0.5, then you will get like a peak along 0.5. And depending on how good your measurement is, so how high your signal to noise ratio is in terms of the detection and how sharply or how precisely you've actually detected the source, you will get either a very sharp or a very wide kind of posterior probability density. And this posterior probability density, posterior because we learn it or we kind of infer it, will tell you what is the actual value. So the peak of the posterior ideally represents the true value. And depending on how precise your measurement is the width of the posterior. So that's what essentially, like, yeah, basically the bulk of what parameter inference is. Yeah.
Okay. How do you apply, in a nutshell, how do you apply bias the bias inference to let's say our parameter inference problem?
So what you do essentially is I'll talk about the standard approach. Let's say the standard approaches that are going on right now, that are popular right now, would be this Markov chain Monte Carlo, nested sampling, all of these. These are terms. I don't want to throw around big terms, but these are just things that these are basically stochastic sampling algorithms. So they can randomly or stochastically sample a parameter space. And what we do is we pose the problem as an inverse problem. So it's an inverse problem. You don't, it's not a forward problem because you don't have the set of parameters, because the forward problem is you have the set of parameters, but you don't know what the data looks like. So you try to understand the function in where you put these parameters, x, y, z, whatever. Let's say the actual function is x plus y plus z. And then you look at the data, how x plus y plus z looks like for certain values of x, y, and z. The inverse model is that you already know x plus y plus z. This is the inverse problem. So you already know x plus y plus z, which is your gravitational wave observation, but you don't know what is x, you don't know what is y, you don't know what is z. You just know that x, y, and z are somehow in there, but you don't know what is x, y, and z, the values. So that's how you pose the problem. So you look at the gravitational wave, that's your x plus y plus z, and you try to find x, y, and z. And x, y, and z here can be the masses, the spins, all the physical properties of the system. How you do this is basically with the likelihood function. So you write down the law, the probabilities law, and then you write down the likelihood function. The likelihood function tells you how this x plus y plus z, which is your data, looks like given some x, y, and z. So the likelihood function will tell you that if you have data which is d, and if you have parameters x, y, and z, then d will be equal to x plus y plus z. And that's what the likelihood function tells you. And then what happens is that you randomly sample values of x, y, and z. So you have some prior assumption, which is called the prior in Bayesian physics, Bayesian probability. So you say, let's say our prior value of x is between 0 and 1. So some random value between 0 and 1. Let's say y lies between 1 and 2, some random values, and z lies between 2 and 3. Why not? Some random values. So it will just pick some random value between all of them. And you can let's say stochastically, so randomly sample some values so that you're not biased to some particular values completely randomly with these algorithms like nested sampling, Monte Carlo Markov chain, Monte Carlo, all of these algorithms. What you can do is stochastically sample these random values and do x plus y plus z and get the data and try to match it with the actual data that you have observed, the gravitational wave. So let's pick some value. Let's pick x equals 0.5, y equals 1.5, z equals 2.5. Add them, make the data, and let's see. Does it match what we are observing? Not really. Let's pick some other value. Not really. And then this way, you do it like millions and millions of times, depending on how complicated the problem is. At some point you see, okay, these kind of values are getting closer and closer to the actual truth. And that's how you get this posterior, this peak. So the peak would be those values that give you the closest approximation to what you have observed. Now that obviously depends on how well you model your likelihood function, which is the x plus y plus z, whether it's actually x plus y plus z, or let's say xy plus yz plus zx or something like this. So knowing that function very well is important. But yeah, so there are other problems associated with that, depending on how well you can characterize the noise that you have, because it's not only the signal, right? There's also noise associated with it. So how well you can characterize the noise, the randomness of the detector noise, and all of these things. So there's a lot there as well, but the basic idea is this. So you pose it as the inverse problem and try to solve it stochastically.
Okay. Is there a way to let's say narrow down this set of parameters, the set of values of parameters that you sample from, meaning you try a narrower set of parameters such that the iteration will be fewer, so you simplify the problem.
Yeah.
Okay.
So ideally you would have prior information about this. So there can be astrophysically motivated priors. So for example, if you see, let's say, a black hole, or let's say a neutron star, right? So one of the parameters is the mass of the neutron star, let's say. In this case, you would not choose the mass to be 50 solar masses, because neutron stars are not that big. So let's say there's a range somewhere between, let's say, 1 solar mass to 3 solar masses or something like this. Then you're already astrophysically a priori, you know that, okay, this is the range that I should be focusing on, because there I already know that neutron stars will not exist. That's one way to do it. But ideally what you would do is you would do this, and then what you would do is like you try to be as agnostic and as unbiased as possible. So you choose like the most widest prior available and so on, and most realistic scenario available. Say, for example, when it comes to measuring the distance or inferring the distance to the source, what we do is we choose a volumetric prior. It's called a volumetric prior. So we just don't, let's say we sample these two black holes merging randomly across the sky, right? We don't do it at the same density. So let's say there's 10 in here, there's 10 in here, 10 in here, and so on. So that will be linear. That's not the case, because the universe also gets bigger as we move further away, right? So there's more area to cover. So you sample 10 here, then it should be maybe 100 here, 1,000 here, and so on, because the circle gets bigger and bigger, the sphere gets bigger and bigger, and so on. So there's this astrophysically motivated, like intelligent choices that you can make in your prior assumption that will help you narrow down your parameter space. But other than that, ideally you would be as agnostic as possible.
Okay, so mainly the let's say the constraint you put given by theory at the end of the day. Pretty much, you know that a source cannot be, you know that the source of gravitational wave cannot be greater than X amount of solar masses, and you, I'd say narrow it down. Wait, okay. And how do you use machine learning for your research? How do you implement it? Let's say, I don't ask if it is helpful, because otherwise you wouldn't be using it. You wouldn't be implementing it. And what are common, let's say, some most common algorithms that you use?
So it is absolutely going to be the next thing that people would use and people would need to use. First of all, let me premise this by saying this basic fact. So these Bayesian stochastic algorithms that kind of solve these parameter inference problems for gravitational waves, they are computationally not very feasible. They take long. So let's say you have a gravitational wave that's about 4 seconds long. That's how long you have observed it for. A typical algorithm parallelized over like a very powerful computer, lots of CPU cores and all of this, would still take order of days. Now, if you have something with smaller masses that kind of, let's say they take longer, so they're like much longer signals. Let's say you have a signal of duration, I don't know, 1 or like some 1 hour or something like this, or like several minutes. Let's say a 10-minute signal instead of 4 seconds. This computational time goes on to order of months, weeks to months. That's totally unrealistic. If you're measuring, so for now we have 90. In the future, if you're measuring gravitational waves every day, like a lot of gravitational waves every day, you cannot wait a month to get the properties of one such source, right? It's totally unrealistic. That is mainly because of the thing that you said earlier, is there a way to actually constrain the space? Because there isn't. There's only so much you can do to constrain the parameter space that you're going to explore. It's totally wide. We're trying to be as agnostic as possible, and doing that stochastic sampling again and again and again, and in order to converge to the actual value, it takes very, very long. And then depending on how sharp your measurement is, how low your signal to noise ratio, or how high your signal to noise ratio is, it can take even longer. So these are unrealistic. So that's why these machine learning approaches have come into play. So they are used in all aspects of detection, basically parameter inference, all of these. So what I specifically do is in parameter inference, and it's a special class of machine learning techniques that I use, which are called simulation-based inference, SBI for short. Simulation-based inference is also known as likelihood-free inference. So there's this beautiful website called simulation-based-inference.org, and they give you all the information about. Basically, it's a great website to go and look at resources about simulation-based inference and what it is. So the idea is, instead of using this likelihood function, we are still solving the same inverse problem that's given by Bayesian statistics, but we are solving it by using a forward simulator. So we are using a forward model to solve an inverse problem. And how you do it, let's say you design a neural network using machine learning, some sort of network with, let's say, linear layers, convolutional layers. These are all these catchy terms that people use. So these are basically, you design a neural network. And what you have is basically some layers that learn your weights and your biases, right? So it kind of extracts information from data. You set up that network, and what you do is you have a simulator designed. So this is what I do, and you have a simulator designed, and that simulator basically can simulate some data given some sort of parameters. So let's say that you give it X, Y, and Z, it will spit out some data D, which is X plus Y plus Z, or something like this. It's just a basic function. But what you do is you simulate, let's say, tens of thousands of it or millions of it. Now what happens is that if you have these millions of these and you show it to the network along with a set of this X, Y, and Z, so you say, hey, these are 3 random values of X, Y, and Z, and this is a random data, which is X plus Y plus Z. Do you think this X, Y, and Z added up, X plus Y plus Z, can produce this data or not? In other words, is this set of X, Y, and Z correlated with this data or not? If the network sees that there's no correlation, forget about it. Look at another example. This looks closer. Look at another example. This looks even better. And so on until it kind of has an idea of what the optimal X, Y, and Z are that corresponds to data D. So that's
how does this save you time?
So how it saves time is basically this comes handy in the case when, so there are several techniques. So one of them is like, let's say there's this technique called amortization, right? So this is one of the important techniques. Why? Amortization is basically what you can do is you can do the simulations and training beforehand, have your trained model, store it, and then doing the actual inference to get the results is instant. It's a second. So you don't need to do it individually for each source. You can just have that and do it again and again. So there are, let's say, two distinct ways in which you can save time. One, if you find a way to carry on and do this stochastic sampling over the entire prior space, so the entire range of possibilities of parameter values that you considered, and then have a stored model like this, then whenever you get some detection, you show it to the stored model, it gives you some X, Y, and Z. That's your parameters. You have another one, give it again, you get another value. So this can be done instantly in the future. So you need to do all of this work only once and then store it and then use it for perpetuity. Now, this has some limitations. Let's say when it comes to what if the noise characteristics of the detector change because the detectors get upgraded, then you have to do the whole process again. But it's still in a way better than what like the current approach of taking much longer is doing. Another way would be to find a way where you can get the same answer, but not having to, let's say, do orders of millions and millions of these evaluations of the likelihood function. And that is what I mainly focus on. And my work is mainly focused on this simulation efficiency part of simulation-based inference, because you should not necessarily, as things get more and more common, these gravitational wave detections get more and more common, you should not necessarily always need like the best supercomputer to do some data analysis for gravitational waves. That's just unrealistic. I mean, look at some galaxy spectrometry or something that you want to do. People can do it on local computers, on some general, like a MacBook Air or some computer that you have. You don't need a supercomputer to do something like this. You should be able to do the same with gravitational waves. We solve the same problem, but you just can't. If you did not need to store these millions and millions of simulations, terabytes and terabytes of data, and you need to do this neural network training, which uses GPUs, lots of CPU power, lots of GPU power, there must be a way to do this. And this is what I focus on. So this is simulation-based, sequential simulation-based inference. So what I do, as compared to the other method, which is this amortizing over the entire parameter space, is you start with a simpler network, which makes your training faster because it's just a less complicated set of parameters that you need to learn. Now, these are not actual source parameters. These are network parameters that I'm talking about. And you start with a set of simulations. What you get is, let's say you start with a possibility of a prior probability of, let's say, 0 to 1 for X, and you want to know what the true value is. You train, you get a posterior peak, which is peaked at, let's say, 0.5, but it starts from 0.2 and it ends at 0.8. So it's very wide. So what you do now, you get the boundaries, 0.2 to 0.8, and you do another round of training. But this time, you don't do 0 to 1, you do 0.2 to 0.8. And then you get again even closer. Then do another round, get even closer. So you zoom in to the actual answer. And after a point, you just hit the level where the signal to noise ratio or the accuracy of your measurement prohibits you from zooming in even further. So that's just the limit. You hit the limit at some point. But
why do you have this limit?
Sorry?
What is sorry for the interruption, but what is this limit?
So this is basically just limited by the amount of noise you have in your data. So if you have no noise data, like very clean data, then you would zoom into some very precise value, right? So you will start with a very prior assumption. Let's say X can lie somewhere between 0 and 1. and you zoom in to the point that you can say X lies somewhere between 0.4999 and 0.50001. So it's the true value is 0.5, but you are so precise in your measurement. But that's not always the case because we have noisy data. So if you can say to the point that X lies somewhere between 0.45 and 0.55, so that's still like zooming into that level. So you can do that at once using the amortized technique that I talked about right before, which will need like a very complicated network. You have to train for very, very long, your machine learning model and all of these things. But this one is much more, let's say, much more basic to do. So you just zoom into the right answer. Basic as in it's simple. I'm not saying it's like very easy thing to do, but it's a simple, and that's the beauty of it, because you kind of zoom into the right answer, and it kind of makes it so that inevitably you're going to get there to the right answer, and you will end up using much less of the simulations or this likelihood evaluation. So what I do is likelihood free, so we don't use the likelihood function, but the forward function, so which actually gives you the random examples of data given X and so on. So yeah.
Okay.
So, yeah.
Okay, so basically you are working onto such that I can do gravitational wave data analysis on my laptop. Thank you, Uddipta.
I'm telling you, it's getting there. And I think even now, for example, if you're interested, I can send you examples where you can work it out on your laptop totally, like very easily. And it will take you, let's say, a couple of hours to get starting from just a blank gravitational wave to having information about all the parameters of its source. Which again is magnificent. And if you have it trained, and there's, let's say, because you zoom in from the bound, like this prior range that you start with. So for example, our X example from 0 to 1, you zoom in, and let's say your final answer is 0.4 to 0.6. So you know that X is somewhere between 0.4 and 0.6. If you now pick another gravitational wave that has X not 0.5, but 0.55, or let's say 0.45, you can still just have the same model and show it the same data, and it will spit out the answer, the next answer, which is 0.55 or 0.45. And that process of actually doing the inference is order of milliseconds. So it's very realistic that you can run it. But in order to have something so powerful, to do it in the previous way, which is the amortized way, you would need a very large model to train. But in the other one, because you're zooming in, you don't need a very large model. You can just use a small model, zoom in a bit, zoom in a bit, zoom in a bit, zoom in a bit, and so on. You don't need to get to the answer at once, but sequentially over time. So
okay. And this the limit you mentioned about the certainty of the about, I'd say, the narrowness of the parameters reminds me of the limit, the uncertainty principle of Heisenberg, and I state now very boldly, we are just the quantum fluctuation within which we can find gravitational waves. We are the disturbance. Okay, but what is let's say the main challenges, the main difficulties that you find in your research? What do you struggle the most with?
So one of the so the thing that I was working on, let's say, for the bulk of my PhD, so for the past 2 years, I spent all my time thinking about one singular thing, and that is building an end-to-end pipeline that you can just show it data and it gives you the parameter. So I built a pipeline, a software which does this parameter inference for gravitational waves, and which uses machine learning. So it's built on top of another algorithm or library called Swift, which basically does this. It's a subset of machine learning algorithms or subset of simulation-based inference algorithm that is called sequential simulation-based inference, or this truncated simulation-based inference. And the other thing is there's some salient features based on it, which I can talk about. But the pipeline that I built along with my collaborators is called peregrine. So peregrine is another bird. We also had lots of fun coming up with the name. So peregrine is a bird. It's I think the fastest animal or something, one of the fastest animals in the world. And it's like a falcon bird, right? It's called peregrine falcon. And the idea with this algorithm is that it uses this sequential method to zoom into the actual answer of the parameter space, and we solve it for a traditional binary black hole compact binary coalescence. But this can be applied to many other problems as well, just by virtue of the fact that it's simulation efficient. So it doesn't need a lot of simulations. So if you have some data that is even more complicated with even more parameters to infer and so on, you don't necessarily need to worry about some very complicated, let's say, storage system or a very complicated computational architecture or anything like that. You can still reasonably run it on a simple machine. And the whole concept behind Peregrine is it uses something called neural ratio estimation. So neural comes from the machine learning part. Ratio estimation is the ratio between the likelihood to the evidence. So that's basically what normalizes the likelihood. And we don't, these methods are also called, the subset of methods are also called simulation-based or likelihood-free, because we don't explicitly write down the likelihood. We don't care about it. We just take the ratio directly, likelihood to evidence. Because this likelihood to evidence, if you look at the Bayes theorem, the equation of the Bayes theorem, it's very like you can just see it anywhere on Google. But the Bayes theorem shows that this likelihood to evidence ratio is also can be equated to the posterior to prior ratio. And if you have the posterior to prior ratio, we already know the priors because that's what prior is. You multiply and then you get the posteriors, right? So that's the ratio that we try to learn. So it's machine learning. So we try to make the machine learn that ratio. And how it learns that ratio is basically, again, by looking at these pairs of randomly sampled values of X, Y, and Z, and one example of the data. And this is a random example, this is a random example. And what the machine tries to understand is whether these two have any correlation between them. Or to put it in more particularly is like whether this data is actually generated by this set of X, Y, and Z or not. So let's say the actual data is where X is 0.5, Y is 1.5, and Z is 2.5. Whether if X is some different value, X, Y, and Z, then and some different data, whether they're actually made from this or is it made from something else. And we show random examples of X, Y, and Z and random examples of data to the network. And it gets more and more knowledgeable over time iteratively, because that's how machine learning works. It trains again and again. It looks at the data examples, random examples of these two again and again. And what it does, it assigns a number between 0 and 1, let's say, whether there's some correlation between them. So let's say it finds like the highest number, 0.99. So then they can say like, okay, this is a set of parameters that is correlated with this data and so on. And then by learning this, what happens is next, when you actually show it some data, after it's learned, you show it some data, which is your gravitational wave in this case, then it automatically knows, we have spent all this time learning about which set of X, Y, and Z is correlated with which set of data. Then now, if you show it some data, then it can easily say, hey, this is a probable value of X, Y, and Z that can be correlated with this data. And that's what it learns, basically. It learns how X, Y, and Z will be correlated with this data. So that whenever it sees some random data, it can tell you this X, Y, and Z looks most probable to be correlated with this data. So that's like the bulk of it. And another salient feature that we do is we do something called marginal neural ratio estimation. So why is it marginal? Because we break down this, let's say this three parameter simple problem of X, Y, and Z. We break it down by marginalizing X over Y and Z, Y over X and Z over X and Y, and make it, break it down into a simpler problem. So what we do is we focus on X at a time and don't worry about the effects of Y and Z. Not by fixing them, we let them vary, but we look at the value of X, and then we focus on Y, then we focus on Z, and so on. This is all done in parallel, of course. These are like technicalities, but in particular, this is what happens in theory. And what this does is, let's say now X, Y, Z is just 3 parameters. Let's say for a standard gravitational wave, actually you have, for binary black holes, you would have 15 parameters for a standard compact binary source. Let's say you have even more complicated signal. Let's say there's like 50 parameters. That's a 50-dimensional problem. 3 parameters already is a 3-point correlation is a 3D problem to solve, right? 50 parameters is a 50-dimensional problem. That's an extremely unbelievably complicated problem to solve. Anyone who has done any mathematics or physics will agree with me that it's just unbelievably complicated, right?
Almost like the dimension predicted by string theory.
There you go. There you go. Another, yeah. I mean, like the best example of this is like I call you to meet. Hey, Francesco, let's meet at 6 p.m. Easy. Now we have a third person that we need to meet. It gets already more complicated. Imagine 50 people and trying to meet at the same time. Unbelievable. So this is what happened. So what we do is instead of solving a 50-dimensional problem, we solve 51-dimensional problems. Much easier to solve. And what you can do is you can parallelize them. You can, let's say you have 50 computer cores, or let's say you have 10. It will still take you much less time than solving one giant 50-dimensional problem if you can solve 51-dimensional problems. So that's the whole principle behind it. And we are not limited to solving only one-dimensional. You can also solve 25 two-dimensional problems, whatever is easier for you. So these are the things that I'm basically thinking about, and that's what I worked on for the last 2 years. And now is the time to do like some interesting physical like physics, some interesting gravitational wave challenging problems, challenging gravitational wave issues like let's say these complicated sources. Let's say some extremely complicated gravitational wave source that has like 50 parameters or 40 parameters, and not just limited to gravitational waves. It can be any problem, any inference problem where you have a lot of parameters or a lot of simulations that you would otherwise need. So all of these problems can be solved by virtue of it being simulation efficient and focusing on this marginalization aspect. So that was the goal of producing this and releasing it to the world, and now attempting to basically apply it to realistic physical problems and showing that, hey, this is let's say very applicable, very reliable, and produces consistent results across a variety of problems. So that was the goal with Peregrine. Yeah.
Okay. What instead about LIGO and gravitational wave detection itself? So what challenges do they face? Because your research area is more onto, okay, I get the gravitational wave, what do I infer from it? Challenges, but what is then the challenge in in detecting the gravitational wave itself?
Absolutely. So in order for me to do anything, I first have to have the gravitational wave. Otherwise, it makes no sense, for sure. There are a lot of
the supply chain.
Exactly. Yeah. I mean, otherwise, I have no point. So the most like the first order challenge is obviously just the amplitudes involved. So as I say it, like the delta changes about 10 to the minus 21. So you need some measurement device that can measure extremely precise things. So it has to be very precise, right? Another thing would be the noise thing. So there's a lot of sources of noise that contribute to this. Even having let's say the mirrors that reflect this light and create this interference pattern and all that, having the mirrors suspended, let's say the suspension system doesn't work and the mirror starts swinging and stuff, that's already like incredible amounts of noise and so on. So it's a very fine-tuned system that they have developed, right? So that already makes it super complicated. Another thing is these detectors are obviously not mobile. These are giant detectors, right? Kilometers and kilometers long. So if you have a source that's, let's say, in a blind spot of the detectors, that's coming from some weird angle where you miss most of the components of the signal. Ideally, you would have it like perfectly so that you get the bulk of it. Let's say if it's at an angle where you don't get it very well, you're basically done. So there's, in terms of detection, there's a lot of challenges, and how these detections are done is also interesting because they have these search pipelines that for the standard compact binary coalescence sources, they do matched filtering. So if you know matched filtering, it's basically the filter is essentially like a model. So you have a model of a gravitational wave. So another one of these forward models, x plus y plus z, something like this. So you have some random parameters, you get a model, and you generate thousands of it so that you have, let's say, multiple possibilities of different types of gravitational waves that you have generated and stored. And what you do when you get some data is that you take a chunk of data and you match all these gravitational waves, these typical gravitational waves that you have stored to your data. Whichever one matches the best, you say, hey, I think it is this type of gravitational wave. Let's do the analysis, and so on. So if your data actually matches with some high degree of probability one of these examples that you have of gravitational waves, then you can safely say that, hey, we have detected a gravitational wave. Now, this has to pass several checks. That, as I said before, that this has to be also detected through multiple detectors and so on, because if it's in one detector, you never know, there can be some coincidence, something, whatever. So all of these things. So understanding what the signal looks like itself is a big challenge, first of all. And that's also some of the reasons why the stochastic things and all these other continuous gravitational waves, all of these things have not yet been detected, because one of the major things is, first of all, in order to detect a gravitational wave, you have to know what it looks like. Otherwise, you won't know even if it passes by you, right? So how do you know this? You find as accurate models of it as possible, theoretically. Now, these are done through these high-end simulations, numerical solvers of general relativity and all these things. And they store this, and then they also use phenomenological theories to kind of generate this. So there's a lot of functions that kind of do this. This has been going on for a while now. And yeah, these are just, again, theoretical predictions. And that's, yeah, basically that tells you how a gravitational wave is supposed to look like. And then what you do when you get something is you just match it to it and then try to get some information. So that's the main thing. And that itself is very challenging, of course, by virtue of the fact that it's usually drowned in data. So it doesn't, in noise, sorry. So it doesn't look like anything. If you just look at the gravitational wave, you cannot essentially say, or you look at the data, you cannot essentially say that there's anything in there that looks like a gravitational wave or something, unless you have something with extremely high signal to noise ratio, that you're lucky that you observe something with, let's say, a very distinct peak. Then you can say, hey, this data definitely has a peak. There's something going on for sure. Otherwise, more for like 99% of the cases or 90% of the cases, it's nothing. It's just noise that you see. So it's somewhere drowned within noise. So you need very strong filtering algorithms, confirmation from other detectors, trying to find it even though it's drowned in noise, all of these things, having a very accurate theoretical prediction of how it should look like, all of these things should be in order to actually detect a gravitational wave, which is also why it was such a big deal. So technologically, and obviously the theoretical romanticism of actually something being detected is there, but technically it's marvelous how it's even possible to detect it, because it's such a fine-tuned system and still so stable to produce consistent detections, right? To give you these consistent detections.
Yeah, it really is. It really is marvelous. But what I'm most fascinated, if I have to be honest, what I am most fascinated by when I think about the gravitational wave itself and the detection of it, is the fact that, as you said before, they do differ from electromagnetic waves because the gravitational wave are specific of the space-time itself. So the fabric, which is, let's say, at the very basis of everything that happens on it. And so, to me, if I think about it and I say, okay, zoom out and look at the universe as it is a drop of water, and I think, okay, the electromagnetic waves, I interpret it as I'd say, some light rays you see through are arisen by events. Whereas gravitational waves, yes, I do interpret them as also in, let's say, arisen created by events, but I do see them as if you were touching the little drop of water, and the water was, let's say, shaking itself in the structure. Okay, and so you have the whole universe which is shaking and in the fabric of the drop of water. And so that is why I find it very fascinating, because I find it much more fundamental about it, because it is really it intrinsically, I would say, implies a movement of the fabric we are lying on, and that's quite
Now imagine detecting this perturbations in the water bubble by being inside the water bubble.
Exactly.
Right?
Exactly.
Crazy.
That is.
And these perturbations are also caused from inside the water bubble. So you are not even touching it from outside. It's causing from inside, and you are inside, and you're trying to detect it. Such a challenge.
That's indeed the thing I wonder. Not that I wonder, but that I would say I try to wrap my hand around it when I think, okay, let's now put into perspective the gravitational wave and the Big Bang. The Big Bang, as one may say, the Big Crunch. Okay, if one believes in a cyclic universe or in a recollapsing universe, the Big Bang couldn't have it been, let's say, someone else touching at the bubble and shaking it, or something else, which forcibly it was outside the universe, because at the t equals 0 at the very beginning, there was no space-time, and so that is why I say, which I actually want to connect now to the question I want to make you now. We said that you mentioned before the sort of things that we expect from gravitational wave astronomy. What do we expect to see? But now I ask you, it has been quite a long time that we have, whether with quantum gravity or all its, let's say, sub-theories, or whatever string theory, or whatever sort of unified theory that we tried to build up. Do you think that gravitational waves in, let's even say, 50 years, okay, may give us a glimpse of what, let's say, not a final, but a more, let's say, a more definite answer of our question at the boundary levels, meaning what is going on in a black hole, what was going on at the Big Bang. We do now have observation. We can now make more theoretical accurate. We can now build more theoretically accurate frameworks to work with. Do you think that may come ultimately, or we will just, quote unquote, we will only, let's say, infer properties from very far away events in the space-time, which are disruptive, or do you think we will ultimately maybe find some definite answer to the big question that we are currently struggling with?
Absolutely. Most of the limitations in trying to understand or make concrete physical conclusions from this data, because now we are in the regime of, let's say, data-driven physics, right? So essentially, there's a paradigm shift starting from like physics-driven observations to kind of data-driven physics, which has its pros and cons. So one has to be very careful in drawing conclusions about physics from data that we observe, because it's highly dependent on the measuring device, the calibrations involved, and the precision and accuracy of your measurement. Now, when we project this in the future, we extrapolate it, we have a very positive point of view, and we always think that this is going to improve because technology is improving, it's definitely going to improve. We don't expect, let's say, mobile phones to go back to keyboards, right? And we assume that this touchscreen thing would actually continue, and so on. So in 50 years, we would actually imagine to have very precise measurements of these things. For example, let's say we develop this algorithm that's very good at denoising gravitational wave sources, for example. And you can actually characterize noise to the level that you can get rid of many of the noise features that you're observing. So you're left with data and very small amounts of noise. That can already help in giving you much more precise measurements. So these precise measurements then give you much more, allow you to make much more stronger claims. Let's say how one black hole in this binary is impacted by the presence of the other, and the ratio of the masses that they have. How, let's say, if you're dealing with a black hole that's supermassive and in the center of a galaxy, how that is impacting the stellar evolution and the evolution of the galaxy itself, and all of these things. So having information about a gross mass function of black holes or these compact stars and so on, getting information about formation roads. So how the stars actually formed and getting independent confirmation than having, let's say, the standard electromagnetic observations, getting information about early universe and so on that's always there. So all these things, I think, will be much more precise. At some point, in my opinion, like most of physics and data-driven science would end up giving you very high confirmation. And there's very high confirmation or very precise conclusion about the same conclusions that we have today. But then there are also theories or statements that we have made from fitting data to observation and like fitting data to theories and so on, where the error bars and the uncertainties in our prediction is so huge that it's not necessarily a prediction by itself. We can make a statement is that like that, if it's a hot day where it rains and it's suddenly gets cloudy at 12 p.m., then X can have a value between 0 and 1. That's a statement that we can make. In 50 years, that statement will be X is 0.5. So something like this. So this can get, your conclusions will get much, much stronger, which then obviously giving a much more precise conclusion in itself is sort of as close as possible to, let's say, a new statement or a new discovery. So there will be lots of these new conclusions that will come up out of it. But in terms of, as I've seen in many other aspects of physics and astrophysics, I don't think it ever stops or you ever reach a point where you can say like we are kind of approaching the boundary of what this kind of research entails in terms of physical conclusions. But what you kind of go is that, let's say, the first 10 to 50 years would be very fast development. And after that, the rate of making this more precise conclusions kind of slows down. And let's say the next very sharp conclusion comes after, let's say, 100 years and so on and so forth. So these things kind of, because even, for example, in gravity or gravitational waves or something, I think after 1915 or so on, after Einstein said, there will be the first 3 to 4 years where I think it was a very active topic of research and people built up on that, even like the next 10, 20 years. But then after that, it had kind of slowed down until and unless 100 years or so on, it actually got detected. And then now again, it's booming and with a different approach and so on. So I think that kind of phase will still be there at some point in the future. But before that, I think I'm super excited because just to have these precise conclusions or more precise conclusions being made in my lifetime, that would possibly change the game. And I cannot wait for it, basically. Yeah,
that's very exciting to hear. And that's I believe the exciting, the fascinating part about physics is that as you proceed, you do not only discover new answers, you discover new questions, and that's a very enticing thing that you basically are always pushing the boundary a bit further, and that's I hope within our lifetime we may be able to assist a major breakthrough as there have been in 20th century with regards to many aspects of physics. So hopefully you may want to come back in some later time and tell us about those new development.
Absolutely, I would be delighted. Yeah, it would be incredible if something amazing happens. Huh? Looking forward to it. I'm sure.
Then, sorry, what did you say?
I mean, I'm sure that something like this will come up in gravitational waves and in many other topics, of course. Yeah, it's just super exciting to be alive. Yeah.
Cross fingered, and we hope to see you back again very soon, hopefully. Okay, but I think it was very exciting conversation. I think we can wrap it up here. I'm done. So I would say I still I am sort of speechless. I am thinking, trying to process all the information.
It's amazing. It's like I'm trying to say as few buzzwords as possible, because it's a field, especially when you combine machine learning and gravitational waves, it's filled with acronyms and these buzzwords and all these things. I'm trying to boil it down as much as possible. But hey, if you want to know more, if you have any questions, feel free to write to me, and I'm happy to talk about research. It's difficult to make me stop when I talk about research, and I just go on forever. So
the only problem is for the one who is listening, who maybe comes at error 404.
Yeah, for sure.
With the brain. Okay. No, I think it was very exciting. I hope people will have liked it. Will have been pleased to hear from you. And so I will thank you for your time. Thank you for your explanation. We can end it here. So thank you. Now I want to pronounce it properly. Uddipta Bhardwaj.
That's very close. Okay. I appreciate it. That's really nice. Yeah.
Okay, great. Then that's good. Probably I mispronounced it at the introduction, but no, I think I actually said
that's a great posterior. That's a very
That's right.
That's great.
Okay. Okay, so I think we can close it here. Thank you, Uddipta, for your participation, and thanks everyone for listening along us. Thanks for being with us, and I will see you in the next episode. Thank you.